Welcome back guys for the UGC lecture program on laser physics under Swayam portal. We had seen in the previous lecture about the laser resonator and how they influence the coherence property of lasers. Now we are going to see, in continuation of what I said earlier, we are going to see the second part. This is about the transverse modes. First and foremost, I must explain what's a longitudinal mode and a transverse mode. Imagine these two represent the laser resonator mirrors, and the laser is coming out in this direction. So the modes which are formed in this direction are called longitudinal modes. The modes which are formed in this direction are in this direction. In a direction perpendicular to the laser beam are called transverse modes. Remember, this kind of things are common in sound wave also. For example, in a big ghatam, for example, in a ghatam, I have seen in Indian music, they have a big pot. In a big pot, they will strike here and there, that is a volume resonator. The modes formed inside will be a variety of transverse modes. This is for the music that comes from a pot. Let us go to the next strip. If you have seen the flute, which will be a straight line one, the air will be blown at one end. There would be an opening the other end, and there will be small holes on the way. Air goes in this direction. Depending upon where the musician or the flutist presses his hand, the frequency of the sound wave will change. There is only one mode, longitudinal mode. There is no transverse mode for the sound produced in a flute, because the flute is about half meter length, maybe the diameter may be 3 or 2 centimeter. I am not very familiar, just seen at a distance. It is about 2 or 3 centimeter. But the wavelength of sound produced will be of the order of 1 or 2 meter. Because of this, you can have only longitudinal modes and not transverse modes. Remember, for a pot, the sound will be bit, if you look at them, the frequency of the wave produced in the pot will be low. Wavelength will be very large, frequency will be very low. On the other hand, in a flute, the frequency will be very high. In a whistle, which will be very, very small, you again produce a single or 1 or 2 modes. All of them are longitudinal modes because the length is very small. The sound comes from a sharp edge. I don't want to go into those details. What is important is the size of the small whistle or the flute is comparable to the size of the wave in the longitudinal direction. So you have only longitudinal modes in flute, whereas in a big pot you will have longitudinal modes and also transverse modes. Now come back to our laser resonator. In a pot you are dealing with the sound wave, and here you are dealing with the light wave. The sound wave with which we are all familiar is of the order of few meters in length, whereas the light wavelength with which we are all familiar are of the order of few nanometers, 1 billion times smaller than the wave with which we are familiar in the sound. But remember, sound wave is a mechanical wave. Light wave is a electromagnetic wave. There are so many other differences. What is important is sound wave is receivable, understandable only by the ear, not by the eye. Light wave is understandable, receivable only by the eye and not by the ear. So these are two different things, but only one point is common, that is both are waves. Big difference is light wave is electromagnetic wave and it's a small wavelength. Sound wave is a mechanical wave, usually of the order of 1 or 2 meters or 1 or 2 centimeters. Now, because it's a small wavelength in light, a laser channel of even 2 millimeter diameter, 3 millimeter diameter is large enough to produce modes in the transverse direction. In this direction or in this direction, they can produce such a modes are called transverse modes. Very often, we end up with multi-transverse mode operation and they are represented by this diagram. Suppose you have very carefully designed single transverse mode laser action, the pattern will be something like in the first one, TEM00, which means transverse electromagnetic wave with no nodes anywhere. You see there is an antinode at the midpoint. How many number of nodes are there? Almost, 0, 0. So we call it as a TEM00. 0 in the x direction, 0 in the y direction. On the other hand, look at the next one. TEM 10 means, look at this one, there is one node somewhere in between. It is like a orange with nothing in between. It is like a 2 slices of orange. You see there is nothing in between. So there is one node. So you say transverse electromagnetic wave with one node in between. So it's called TEM10. Look at the next one, or just down straight. It is a TEM11 node. Here there is one in the x direction, one in the y direction. So it is called TEM10 mode. Like that, there are so many of them. You can take a look at more carefully later. What we want is only TEM00 mode. It is a bit difficult to get it, but what can be done is, if you have a small hole, small aperture in the laser path, most of the extraneous TEM0, TEM11, TEM20 modes could be easily cut off. You will have more or less TEM00 mode, and that kind of TEM00 mode, as shown in the diagram, will have an intensity profile of Gaussian nature. A Gaussian nature means is, at the midpoint, the intensity will be very high. Compared to the intensity at the midpoint, all the sides will be exponentially falling off. It will be rapidly coming down. That is why we say it's a Gaussian profile. The intensity will be R square. Intensity will be falling off R square. That means at the tail end, it will be very, very small, 1 or 2% only. Most of the light would be concentrated along the axis. That is what is shown in the TEM00. This is the best kind of laser for a lot of applications, particularly for material processing, metal cutting. If you have this kind of mode, for example, in CO2 laser, we always try to have the TEM00 mode or a neodymium laser. These are the two lasers best for all material processing applications, about which we will see later in great detail. For both of them, we try to have 00 mode, so that when we try to focus using a lens, the focal point will be very, very sharp. If the focal point is very sharp, the intensity, that is the power per unit area, will be very high, and that is capable of generating a large amount of heat, which will cut a metal or a wood just like that, just like a knife cutting your banana. A CO2 laser will cut a metal just like banana. You will see later those details, and that for that kind of laser you need TM00 mode, and the intensity profile is as shown. Now, keeping all these together, what is the realistic condition is, all these things are more or less ideal condition. The realistic condition is, very often we define something called M square about the quality of laser beam. For TM0 mode, it is M, that will be 1, while multi-mode diodes will have M2, some of them will be 100. All these problems are always there, particularly for diode laser. As you have more and more TM10, 20, 30, there will be certain spread in the frequency. Because of this one, the quality, the coherence property of all these higher order laser modes will be going down and down. YAG for a helium ion laser, it is very easy to have a very good TM00 mode with single mode, single longitudinal mode action also. On the other hand, for a laser, solid state laser like titanium sapphire or neodymium glass laser, the bandwidth is so high that at any time you will always work with high bandwidth laser action. Now, the funny point is, scientists have made use of this disadvantage. They have converted the disadvantage into an advantage by making use of large bandwidth lasers to produce ultra fast picosecond lasers. Greater the bandwidth, you can lock, you can bring many modes come together, behave in a certain proper fashion, that's called mode locking. More the number of modes locked together, it is something like more number of people pulling together simultaneously a big cart. Imagine that your car got stuck somewhere and you are struggling to push it or take it out from the mess. Alone you may not be able to. Then all of a sudden some people who are walking along there, they won't help you. Some 2 or 3 people come and push. Somebody push, somebody pull. Now imagine all of a sudden 10, 20 people will come. Then the car will easily move very fast. In a similar fashion, when you pull or push, you always say, you make some sound, something like that. Then you say, all of them put together, say Then they will put all the rippers together. Then the car which got stuck somewhere in the pit will just jump up and start rolling up. We do same thing for Ti-sapphire laser. We lock a large number of modes together, come to some kind of understanding, go interference in time, they behave all of a sudden, they develop certain understanding among themselves, put all the modes together, convert into a picosecond pulses of very sharp peak power and a very small bandwidth in time as well as in frequency. Because of this kind of advantage, they are useful for ultra fast phenomena. You can of course use additional filters like birefringent mirrors. There are light filters, there are so many of them. Maybe if you are really interested, you can do higher studies in this area and then you can become an expert in laser technology. It's a very fast developing technology and it has very great innovations in so many fields. For a stable frequency laser, one such laser which is very much required, as I told you, for gravitation wave detection is the whole laser will be stable, mechanically stable, thermally stable, electrically stable, electronically stable, and there will be a servo mechanism to make any correction here and there and make a perfect alignment of resonator mirrors. The resonator mirror under ordinary condition will not remain same, because there will be a vibration, there will be some heat, so they will just move back and forth. So you must have certain type of servo mechanism to make the correction and then make it very rigid. Then the laser that comes out with a single frequency, and the single frequency will be stable for few days together. That kind of stable frequency lasers act as an atomic clock, and there are so many applications for them. We will come back to that one later. I have told you just so far a laser with two plain parallel mirrors. They are called Fabry-Perot mirrors. They are the simplest one to imagine and understand. But there are so many other designs depending upon the requirement, and I am just showing some of common resonator mirrors, mirror configuration, resonator mirror configuration. First one is a plain parallel resonator. Second one is called concentric resonator. That means you have two concave mirrors with the radius of curvature of left side mirror is on this on the center. I mean, both the concave mirrors will have the midpoint concentric, the center of curvature will be common, that is called concentric resonator mirror. This is one configuration. Another interesting configuration is semi-concentric resonator. Let us see more. There are so many varieties. Let us, you see plain parallel, plain mirror cavity. Now you can see variety of mirror resonator configurations. The top one is a plain parallel, which we have discussed so many times. The next one, you can focus on the right red light one, so it's easy to understand. This is a spherical mirror with midpoint, the center of curvature of the concave mirror joining together. That's concentric. Another one is a long radius mirror. Below that you have a confocal configuration. Confocal means, you know, one mirror will have certain focal point. This mirror will have another focal point. When the focal point come together, superpose one over another, that's called a confocal resonator configuration. Another one is hemispherical. In this case, left side mirror is slightly concave and the right side mirror is a plane mirror, so that the center of this one, center of this concave mirror falls on this plane mirror. So you will have a kind of cone. The shape of the light inside the resonator will be some kind of a cone with this coinciding with the curvature. That is called hemispherical. Similarly, you can just pull it off, then you can have a long radius hemispherical. Next one, there are so many of them. All depend upon the nature of the medium, pumping configuration, and above all, what kind of applications required. Mostly, depending upon the applications, the resonator mirrors are carefully chosen and designed. All this time, I have been giving you mostly qualitative, figurative, representative picture of laser resonators. Let us have a little bit of theory also. The number of modes in a volume resonator, according to Planck's theory, is given by, this is the total number of modes. Then the mode density per unit volume per unit frequency interval is obtained by differentiating Nm. Then you will have 8 pi nu square over C cube over C cube. Okay. Now, under this condition, you will have enormous number of, a large number of modes. This is the representation of a cube, which is a 3-dimensional volume resonator. If you want to understand, I can give a very good example. You take a wooden box of 5 centimeter by 10 centimeter by 7 centimeter, something like any rectangular box. You can easily find somewhere. Keep it close, then just tap it on left side, right side. You will have a rough sound. You will have a sound which will be of very low frequency of long wavelength, because you will generate a number of frequencies along x direction, along y direction, along z direction, and all of them will be on a low frequency mode. The rectangular box shown there act as a volume resonator. Remember, some of you must have seen what is inside your microwave, which you use for making your chicken or any rice for cooking. That will be more or less like this one, a rectangular box. In that, you will have a microwave generator. Microwave means it's an electromagnetic wave or micrometer wavelength size. That's the meaning of this microwave. That means the length of a wave, electromagnetic wave, will be 3 centimeter, 5 centimeter, 10 centimeter, something like that. Such a microwave will produce a wave in this direction, in this direction, in this direction, in this direction also. Their common microwave used in the kitchen is a volume generator. There you could have seen a metal reflector also. If you take such a microwave resonator for our laser, you will see a large number of modes are competing for each other, and then it becomes a volume resonator. Such a volume resonator is something which should not be used for laser. We call them as an open resonator. An open resonator will have a configuration like this. A typical laser resonator is something like this, which you have already explained. Here you will see two mirrors, and the light wave is going like this one only along z direction, along other direction, along y direction or along x direction. No mode is formed because it is kept open, no light is reflected. So it becomes a single dimensional open resonator. We start with the open resonator for all laser process. This itself is a very bright idea. Then already I have shown you plain parallel resonator. We will consider a slight mathematical ideas. These Fox and Lee are the two scientists who worked about the theoretical background for this one. What he said is, he started with this one. Let us start a light wave getting reflected in mirror M1. After reflection, the reflected wave will have a profile as shown below, which will be a hemispherical, and as it expands, it becomes more and more hemispheric, bigger hemisphere. Now look at it, that the first reflection between M1 and M2, it will be a hemispherical. After 10 reflection back and forth, you see it becomes more elliptical, or it becomes more directional, intensity or amplitude more concentrated along the longitudinal axis. This is because of repeated diffraction focuses the light all along the axis. That's the meaning of this one. Then they started with the theory like this. They started the intensity. If you represent intensity along x1 and y1 at some point in the mirror, it's a plain parallel mirror, open resonator, reflection is only along z axis. 2a represents the diameter or A represents the radius of this mirror or half distance of the mirror M1, something similar in this one. Then if we start with the P1 representing the amplitude of the wave at x1, y1 on some arbitrary point, and if P2 is another point in M2, another point of the mirror at certain angle theta at a distance d. The question is, are they correlated? The wave pattern in P1 and the P2, are they correlated or not? Is there any kind of relation between the 2 points in terms of the wave nature? They worked out with this kind of, they started with the complex electromagnetic field given by this equation 5.1 taken from my textbook. n1, n plus 1 represent the wave amplitude or representation of the wave at x2, y2, which I have already defined, is equal to minus I k 4 pi, that is integral all this put together. You can easily see un represent the amplitude of the wave at the point u given by x and y, x1, y1. Then they are separated at distance of r at an angle of theta. Then this is the starting point. Then they said, if I start with this one and allow the wave to go back and forth, and then they calculated for a open rectangular mirror, then they said when t is equal to 0, that is number of transit is equal to 0 or number of transit is 1 or 2, you see the first top figure says the amplitude on the face of the wave is totally random. Totally random. They cannot predict anything about the amplitude or the phase or the frequency of the wave. On the other hand, if the light is going back and forth 300 times, then you see there is a decrease at the 300th iteration. But what is important is the amplitude and the phase of the wave at two different points of the mirror are correlated. There is a phase correlation. This kind of phase correlation represents there is a coherence between the 2 points. The spatially separated two mirrors become correlated, or they become, the wavefront becomes coherent after sufficient number of iteration. For example, t is equal to 300 iteration. Now the question is, how can you get 300 iteration? If you can get a 300 iteration, you can, whatever you predict is understandable. In principle, this is what the theory showed. In practice, it is easy to realize. Let me explain. Imagine that the distance between the two mirrors is about 15 centimeter. Then for one complete iteration, the total distance covered is 30 centimeter. 30 centimeter would be covered by the light in 1 nanosecond, or the time between the wave at this point and the wave at another point of the mirror after 1 nanosecond, it will be after 1 nanosecond. It takes only 1 nanosecond to come back. Let me repeat. Suppose I look at the point in the mirror at this point. Then it will go, come back to the same point after 1 nanosecond if the distance between the mirrors is 15 centimeter. Now point is, after 300 iteration, they go back, come back. After 300 iteration, how much time it would take? After 300 iteration, you would have taken 300 nanosecond. After 300 nanosecond, after the wave that is starting will have certain correlation to the wave that comes back. Not only that, the wave that is starting from here, is correlated to any other point in another mirror also. All these are possible. If sufficient number of iterations are done, then you will have a phase correlation. You can see at the bottom picture, you will see after 300 transit, you will see the amplitude fluctuation changes. Initially amplitude will be random, zigzag. After some time, you will have certain correlation between one point of the mirror and another point of the mirror. That means they become coherent for sufficient number of time. That is what they call mixing of waves because of stimulated emission. Remember, because of stimulated emission, by repeated training, the waves gets mixed up, the waves get trained up, then because of the repeated diffraction, you can see the wave becomes very, very directional as shown by the bottom representation. You see the wave that comes out of the mirror M2, look at this carefully, is a Gaussian beam because of the diffraction, repeated diffraction, and this is the Gaussian beam, and that is what you see in most of the lasers which I have already explained. Now, whatever they have been able to give a model has been realized very often in most of the lasers, most of the real lasers. That means what you predict is realized in reality. That means this kind of model is understandable, this kind of model is working, or the theoretical interpretation, theoretical expectation and experimental measurement both tally together. That means this kind of plain parallel open resonator is the best for any kind of laser process, because light has a frequency of the order of 10 power 14 to 10 power 15 hertz, because the light wavelength is typically 500 nanometer, which is the green one, which is a very high frequency or a very short wavelength of 500 nanometer. For this kind of electromagnetic wave, wire will not help, this kind of microwave type will not help, microwave resonator will not help, volume resonator will not help, only the open resonator. Open resonator means light is not allowed to form along this direction or this direction. Light is allowed to form interference, diffraction only along this particular direction. Then what comes out is a spatially coherent, temporally coherent light, and that is a laser. Thank you very much.